Good morning, everybody. So today, time for me to tell you about a little bit about terahertz optics and terahertz optical elements. I hope we will go smoothly, and we will try to make a small break more or less in the middle. So I come from Faculty of Physics in Warsaw University of Technology. We have a very, very beautiful building, nice to study there, nice to work there and do some research. I would like to also acknowledge Military University of Technology and Center for Physical Sciences and Technology, because lately these are the people with whom I'm cooperating really a lot. And my last research is done with a group, like actually among these groups. So we will start with a small outline of my talk. We have a lot of points, and we will go one after another through these small little points. They are not equally divided, so some of them are a little bit longer, some of them are a little bit shorter. We will start from telling about reflection, refraction, and diffraction. Then we will talk a little bit about diffractive optical elements. We will go through the other possibility of designing thin structures. We will discuss manufacturing methods of terahertz optical elements. We will discuss also materials that can be used. We will go through different types of elements. What can we do? How can we form the light or radiation? And we will discuss a little bit what we can and what we can't do with such types of elements. And at the end, we will have some discussion about imaging setups or optical setups in terahertz for terahertz radiation, and some small application of elements dedicated to particular setup, realizing some features that we wanted to obtain. So at first we will talk about somehow goal and motivation, because terahertz radiation started to expand last 35 years. It is very, very big growth. And at the beginning, all the time, we were talking about emitters and detectors and nothing in between. To properly shape the beam, to form, to redirect it, we need some optical elements in between these emitters and detectors. And we would like to be them as compact and lightweight as possible. We would like to have possibility of fast prototyping. Here you would see that we need some elements that have large diameters and short focal length, and this is some issue that we will discuss also, like how to make them and what are the problems. It would be great to have the availability to manufacture your elements in your laboratories, just to design them for yourself. And we would like to also have some elements that are not very, very expensive. They're just small enough. They are tailored just to your needs. And somehow in terahertz world, this is quite achievable. With this motivation, we can start the story. And now we will go to to talking about three different phenomena: reflection, refraction, and diffraction, because they will tell us about three different types of optical elements. So at the very beginning, we must say that optics, it is not only glasses. This is the first question I always tell when I'm speaking, that I'm after when I'm dealing with optics. Oh, so you mean you're designing glasses? I could, but no, I don't do it. At first, different types of optical elements. We can use three different phenomena, as I said: reflection, refraction, and diffraction. Depending on which type of design we would choose, we will make the element in a different way. So at first we would go to terahertz mirrors. I will focus mostly on terahertz optics, but mirrors would be working also at other ranges of radiation in the same manner. So we use the phenomenon of reflection. This is relatively easy to design because we need to use ray tracing. So we are treating our radiation as rays and reflecting them from the surface that is flat or not flat. Here we have off-axis parabolic mirrors. And they look very, very similar as the one used in visible, but here they can be 3D printed and covered with aluminum, gold, or different other metallic coatings that would reflect our radiation. And this is possible because the surface roughness of good quality optics should be at least λ/4. λ/20 is a very, very good optical element with this proper smoothness. So this is achievable in terahertz range, also using 3D printing. So here this cost of such mirror is much smaller than in case of visible light. Now the second type of elements that is dealing also with radiation as rays is refractive elements. So we use the refraction in between two media and we just design them using ray tracing. Of course, we can optimize both surfaces to create more or less achromatic or without some aberrations element. But nevertheless, the idea of designing such element is relatively easy. If we would jump to terahertz refractive elements, we would mostly see some lenses. Here, the most probably most of you would see silicone lenses that are relatively bulky, big. Even if we don't use these silicone hemispherical lenses, other types of lenses are also relatively thick. And now, in some moment, thickness is good, not in case, for example, for silicon, it is very transparent, so it doesn't attenuate a lot of radiation. But if you would use different optical materials, it doesn't have to be so transparent. So we would like to make this lens a little bit thinner. And now the discussion is like how to make it thinner, because not always we have so much place to put it. So the idea is coming from Fresnel, who invented the possibility to make the lens thinner. The lenses, for example, that are used in lighthouses. So we weren't able to manufacture, actually, because to design is easy, but we weren't able to manufacture such big, bulky glass glass lenses. So the idea was to make it smaller and to like get out of the middle of the lens. And it happens for many, many years. It works in many lighthouses. You can see such types of lenses. And now we would go, because we have also such elements as you see here on the right-hand side. So they are somehow similar and somehow different. The similarities is that they look kind of similar, but the design method is totally different. And on the left, we have ray tracing method. So the elements are having the thickness of thousands of wavelengths. And here on the right-hand side, we have the diffractive design. So we have a wave approach to our element, and the thickness is around the wavelengths, single wavelengths. So looks similar, but these are two totally different elements. And now we will smoothly go to this lenses and other elements that can be designed in a diffractive way. If we would compare, here we have the regular refractive structure which for big diameters and small focal lengths starts to be very, very thick. If we would design it in a little bit different way, so this element will be flat. We'll have continuous phase profile, and the difference in between these two elements manufactured and realizing the same, having the same optical parameters is shown here. So this is a refractive one and diffractive. We can see that this one is much thinner. And now how we would design such type of elements, and we know that refractive elements, we use ray tracing, so we treat our radiation as a ray. And in diffractive way, we would use a wave approach. So here we have refractive elements that are mostly a little bit thicker just due to the design method. And here we assume that we have the radiation that we can describe it as a wave. So we have a divergent convergent beam, and our element would, for example, focus plane wave here. So we will tell about the about amplitude and phase of our radiation. So to talk about it, we will discuss and we will describe our wave as having some amplitude profile and some phase profile. Here we have the light field distribution of our wave after our element, and we will have amplitude distribution, and we will have phase distribution. So all this function will tell us about the transmittance of my element. And now we will talk about refractive and diffractive. We will come actually from refractive to diffractive elements. As you can see here, we have this big bulky element. We have the Fresnel lens that was used in lighthouses, so designed in a totally different way. And we will have a kind of structure which looks similar, the one that were in the photograph shown a few slides before, that is similar, but all these elements will be designed in a different way. So here we will focus on the fact that after our element, we want to have our phase distribution, our desired phase distribution, and all of these elements would introduce such phase shift of the radiation to create particular phase distribution after our element. So if we want to have a converging lens, we would have the distribution that is shown here. It will be from black to white, from 0 to 2 pi. And this structure would introduce phase delay that will create such phase distribution just after it. Now a little bit about advantages and disadvantages of all these three groups of elements, because none of this group is the best. It depends on our needs, and it depends on the application, and we would use just particular elements for different applications. Mirror optics is somehow expensive and difficult to maintain. If we 3D print it for terahertz radiation, then it is cheaper. But there is a huge advantage of mirror optics. It is no chromatic aberration. So it means that our mirrors would work the same for visible, for infrared, and for terahertz radiation. Of course, if we have the surface that is reflecting all these ranges of radiation. But this gives us huge possibility, and in many spectrometers we are using mirrors because they are achromatic. And of course, because they have good reflecting surfaces, so we will have low losses. If we come to refractive optics, they are much easier to put into the system, to align, to maintain. We will use them in our optical setups. In case when they are becoming thick, we start to have big losses. So here we have amplitude in assumption that we have no losses. But if we would have such lens and assume absorption coefficient of our material around 2, so then we will have huge losses in the middle, which we will not have for diffractive element, which will be just thinner. But the difference in between refractive and diffractive optical elements, which is very, very significant, is that diffractive elements are designed for particular wavelength. So they somehow have a big chromatic aberration because they would work the best for our designed wavelength. So we are dedicated to choose the wavelength we want to work with. However, the thickness of the element is much smaller, and this is just visibly thinner and more light wave and more compact. And now if we would do some experiment and ask Google about terahertz optics, terahertz lenses. So this is what I got yesterday for such a request. You see that all these lenses are relatively big and rather bulky. They have no very big diameters. So in some applications, there really is a big need to use diffractive optical elements. And this is the next part of this presentation, to describe how we can design diffractive optical elements and how they work. So diffractive optical elements, as I told at the beginning, they would introduce a phase delay after my element. Here we have the example of just converging lens. We have the transmittance of our element. So this element would introduce such phase distribution after our element. Here we have wave number, we have radial coordinate of my element, and we have a focal length. This transmittance is given in off-axis approach. And why is it given here as an example? Why we need this off-axis approach in terahertz range, we will discuss a little bit later. So we would translate this phase delay map that we want to obtain after the element into our element. And how we are translating it? We are using the phase delay we want to obtain in relation with thickness of the material. Here is some example. We are calculating the maximal height of our element, and we must take into account that we will have some substrate layer, because here we would have like no thickness, so the element wouldn't be stable in one, and it wouldn't be in one piece. It would just broke into many different elements. And mostly here we are assuming that we are in the air, so we have one here. This is the refractive index of our material, and this formula allows me to translate the phase delay map into real manufactured element. And this is one of the elements, we call them kinoforms. So we call them the elements that are introducing continuous phase changes. So you see that we have relatively complicated structure. Not always we are able to manufacture such elements. So what we can do, we can design it in a different way. If we have the possibility to manufacture the element having this continuous phase profile, so-called kinoform or diffractive Fresnel lens, so we are doing it. But if we don't have such possibility, so we can code this type of phase distribution into multi-level structure, into binary structure manufactured from one material with air gaps, or the binary structure manufactured with materials with two different refractive indices, or just the amplitude structure. So if we would translate this phase delay map and we would obtain this continuous phase profile, so then we can just code it also as a binary element or step-like element. And now here what we would like to choose, of course, the smooth one, yes, the kinoform structure, that is a phase structure, so it is very, very transparent. And the difference in between these elements will be the efficiency of our element. If we have easier manufacturing, so then the efficiency of our element will be smaller, but it will be cheaper to manufacture the element. Sometimes we have no possibility to have the materials introducing phase delay without attenuation, so we are forced to use amplitude structures, and mostly such issue is in EUV because there we have not many materials that are very transparent. But in terahertz range, we are happy enough because in actually almost in all cases we can design and fabricate elements with continuous phase profile. And now discussing the efficiency, probably some of you think like, okay, what is the efficiency of my element? So then we should think about the diffraction grating, because diffraction is the phenomenon we are using here. So if we have the transmittance of my grating, it can be different. And diffraction grating would divide our incoming radiation into diffractive orders. And now if you would take the light field distribution impinging our diffraction grating, then we would take the transmittance of our element and we can expand one period of my grating into a Fourier series. So then I would result in the transmittance of our element as the series having some coefficients. Here we have coefficient given with this formula. And if we would calculate this coefficient, so they would tell me how much of radiation will go into which diffractive order. And this is actually the definition of my efficiency. And now you think, I thought that, but how to translate it into the efficiency of my diffractive element? Because it is evident that we would use different distribution of energy in these spots for different types of diffraction gratings. And actually, it transforms exactly to our diffractive elements. Because we would, if we have our diffractive element coded in a particular way, so it could be binary step-like or with continuous phase profile. So the sum of the incident radiation would just go through, and this one corresponds to the radiation that in a diffraction grating goes to the 0th order. Some of the radiation will be focused in the desired place, if this is a focusing lens, which is an example here. So some of the radiation will be focused in the place where we want to have the focal spot. And this is corresponding to the plus 1st order, and then we have plus 2nd, plus 3rd order, which will be focused a little bit closer. And then we have another minus 1st, 2nd, 3rd, or other orders of diffraction that will be divergent after my element. So what I would like to have actually is to have the incident plane wave and to focus everything in our focal spot. And this solution would give me only one of these elements. This would be the element with continuous phase profile. So if we have the element that is a kinoform structure with continuous phase profile, we can also have binary element or amplitude element. So these three elements, now you know that will have different efficiency. It's easy to guess that amplitude element will have the smallest efficiency, binary phase element will have somewhere in the middle, and this will have the biggest efficiency. Now, the only comment here in between these two elements is that please note that here we have the phase delay introduced by such element from 0 to 2 pi. And if we are creating a binary element, we must introduce here a phase delay of pi, because if we would introduce from 0 to 2 pi, so then 0 and 2 pi is no phase difference. So here we must be aware and cautious if we are designing binary elements, and we must remember about it. And now some numbers that are related with our diffractive elements. If we have kinoforms, they will have 100% of efficiency, in theory, of course. This is diffractive efficiency, so it means that all the radiation will be redirected into our focal spot. If we will have multi-level phase structures, depending how many steps they have, so if it would be a 4-step structure, it will be 81% redirected in our focal spot. But you can see that in 8 or 16 levels of our step-like element, we are reaching almost 100%, because we are reaching 99%. So multi-level elements are also very, very good if we are not able to design them in a continuous way. If we have a binary phase element, so only 2 different levels, so it will end up with 40% of energy redirected into our focal spot. So it means that 60% is lost elsewhere, so is forming actually a noise, because some of it will be focused a little bit closer, some of it will pass through the structure without let's say, being bent, and some will be divergent, so it will, all these other orders of diffraction actually are forming noise. And as you can see at the top, amplitude binary elements have the lowest possible here efficiency, only 10%, but in some ranges of radiation, they are the only solution. And now I talked a little bit about diffraction efficiency, which tells me how good my diffractive element is. But here, in all these cases, we assume that we have no attenuation of our medium, which is not the case in real life. So if we will talk about something which is called real efficiency, so we must take into account at least two things. We must take into account absorption coefficient of our material, and we must take something which is called Fresnel losses. Fresnel losses are how much of the radiation at the interface in between two media is reflected back, and it depends on the difference of the refractive indices in between these two media. So here we have different colors and two graphs. On the left-hand side, we have attenuation that is small of my material. On the right-hand side, we have the diagram with material of having much bigger attenuation. So these blue curves are the same in two cases, because they are showing me diffractive efficiency of my binary grating. So it goes up to 40%. If I would think that, okay, I am using the element, the material that has refractive index 1.5, so then this green line tells me that I am losing some energy because I have also this reflection from the surface. If the material would have bigger refractive index, for example 3.4, so then only Fresnel losses will attenuate would reflect back my radiation, and then we are ending with this pink curve. This is not a random number, because 1.5 is most of the polymers, most of the materials used in optics have the refractive index around 1.5, and 3.4 is the refractive index of silicon. So using silicon lenses, you must bear in mind that the reflection from the first surface, from the interface between air and silicon, would steal you a lot of energy, because silicon has big refractive index, so Fresnel losses are big. If we would think about the attenuation of my element, so we have attenuation for two different elements, which will be this like orange and red curve. So for the materials with smaller attenuation, we have more efficiency. With bigger attenuation, we have less efficiency. And if we would take into account both parameters, attenuation and Fresnel losses, so we end up with these yellow and violet curves. So yellow curve here is telling me about real efficiency if I would introduce attenuation and Fresnel losses. And this violet is for just bigger refractive index. If we would think about big attenuation and big refractive index, so this violet curve here, we see that this efficiency, effective efficiency, is the biggest not for the phase shift of a pi, but for a smaller phase shift. And in case of, for example, EUV materials, we are somehow making them thinner, not to work exactly properly in the theory, but to attenuate less. So the total effective efficiency of our element will be bigger than for the thicker element that would also attenuate a lot. So depending on the on which hand side we are, if we have transparent materials or not transparent, we also have to bear in mind that this design process can be optimized. And now we are going to the comparison of refractive and diffractive element. If we would plot just it as a converging lens, so we see that in both cases we have a focal spot, but the element is thinner. Here we have the comparison of axicon structure. Here is the refractive one, here is the diffractive. The light field distribution after the element is very similar, but this diffractive element is much thinner. And now also a little bit about other thin structures, because we can use different types of designing. Here we have the wave approach, but at some point we can go to subwave structures. So all these details will be smaller than the wavelength, and this is totally different designing method, which we will not discuss here because we will not finish our lecture in proper time. Also, another method that is forming thin elements is using metamaterial structures. They are also designed in a different way, but they assure that our element is thin. And if you would see here, so the lens designed with this small cross-like structure would have the similar functioning parameters as the binary one. So these kind of subwave and metamaterial structures are also possible to form the thin structures. The question is about efficiency, but some of them are better, some of them are worse. And this is also the possible use. And now, if we are in terahertz range, we will go to manufacturing methods. It is here actually nice and easy because we can use different methods to manufacture our optical elements. We can use etching, which is I think maybe one of the most expensive methods here, but we can use milling. so we will drill our element. We can use 3D printing. So we can print from filament. So fused deposition modeling 3D printers. Also, we can use selective laser sintering with a powder. So this is this case. So we are applying the layers of powder and using UV to make it glue to each other. We can use cutting, laser cutting, and here we have the example here and here. We can use also sculpturing, because this is also a terahertz lens that is made out of stone. And all these methods actually allows us to create very like cost-efficient elements. If we would think about 3D printing, at the very beginning, we were transforming our phase delay map into the either the element or the mold to create our element. And at the very beginning, we were trying to use different type of coding to have the bigger zones and a little bit thicker elements to be able to 3D print them. But with time and with different materials and proper parameters of our 3D printer, we don't need to, let's say, form more like bigger elements. Actually, here we can 3D print the lens. These are the lenses designed for 1 terahertz. They are 3D printed and they are working. Here you have different parameters of the lenses, so the diameter and the focal length. And you can see that they are relatively big and they have relatively small focal lengths. So in the refractive version, they would be very, very thick. And now if we already have this possibility of manufacturing, so we must think a little bit about the materials that we can use in terahertz range. And using different types of materials tells me a little bit about the properties of my element. I divided terahertz materials into different groups. We have one group with relatively high refractive index, and here, for example, we have silicon, which has the refractive index 3.4. So here, the thickness of elements will be small because we have big refractive index, but we will have big Fresnel losses, which we must just have in mind while designing our elements. We have the materials, not very big groups, big group having the refractive index around 2, a little bit more. So for example, here we have quartz, and we have a whole group of materials with a refractive index of 1.5. And here we have different polymers, and we have polyethylenes, high density polyethylene, we have Teflon, we have this terrible, namely TPX. The real name I even don't try to read. We have Tsuripika. So we have different possibilities, and this group is quite big. The possibility of having the refractive index of 1.5 is similar as glass for visible light. So when we are making using glass, so this would be the whole group of materials that works in a similar way. And here also we have a lot of materials that can be 3D printed and are also transparent for terahertz radiation and have also refractive index similar to more or less 1.5. And now if we are talking about 3D printing or not 3D printing, having any material that can be used in terahertz optical elements. So what we are doing, we are plotting their parameters, their refractive index and absorption coefficient into a graphs, and we are having groups of materials. As you can see, like the most popularly used PLA is having a really bit bigger refractive index and bigger attenuation than, for example, polypropylenes that are down here. So we have different varieties of materials that can be used for terahertz radiation, and defining the refractive index and absorption coefficient for particular wavelength can be realized in time domain spectroscopy. I will not discuss the functioning of time domain spectroscopy because it was already done, but in terms of optical person and visible light recording registering, time domain spectroscopy has one very crucial feature. It registers signal that is proportional to the electric field, not to the intensity. So having our signal registered point by point, this pulse will tell me about amplitude and phase of my radiation, not only intensity. So out of one signal, I will be able to determine refractive index and absorption coefficient along whole frequency range. And coming from visible light to terahertz, this looks like a wonderland. So this is some examples of the materials, how we are checking if it is what parameters it has. At the top we have reference pulse and terahertz pulse with passing by the material with different thicknesses. Then we have absorption coefficient, transmittance, and power spectrum density actually of our signal. And now on the left-hand side, we are not using any windowing. On the right-hand side, we are using windowing. As you can see here, actually in all these three graphs, if we are not windowing, so smaller thicknesses are introducing this wavy kind structure, which is not actually proper value of transmittance or absorption coefficient or refractive index. This wavy-like behavior comes from the fact that we have the second reflection, second pulse here, and it forms me this wavy-like structure. Here, if we are windowing, so it means that we are removing this second reflection. So for all three thicknesses, we are able to avoid, suppress the influence of this second reflection. For the thinnest one, we are not able to do it. So the idea for us that we should take home after looking at this graph is that if we want to correctly determine refractive index and absorption coefficient of our material, we also need good thickness of the sample to remove the second reflection that is forming this wavy-like behavior of my element. And now we are plotting refractive index, which are this refractive index value, which are these dashed lines, and absorption coefficient values, which are these solid lines for different materials. Of course, these refractive index values for many polyamides in terahertz range have relatively low dispersion. So for each wavelength or each frequency, they have very similar value. If we are looking at the absorption coefficient, we want to have it as low as possible. And here you would see that the lowest one is HDPE, which is commonly used as a material for terahertz range, but also paraffin. Paraffin is very transparent, and it is very easy accessible material. So if you are able to 3D print mold for your lens and you have a candle, so then you will have a very good quality optical element in your laboratory. Of course, we have other materials that are used here. For example, we have polyamide 12, which is this violet one, and many 3D printed materials are also here in between, which are not plotted here, but we also measured their properties. And if we are talking about molding and creating our elements by designing a mold. So here I named paraffin, but I also would like to, let's say, wake you up a little bit and tell that not only paraffin can be used, we can also use chocolate, because chocolate, as you can see, has a refractive index more or less 1.7 for in terahertz range. It has some absorption coefficient. Maybe it's not very transparent as paraffin, but it is also transparent. So such chocolate lens focuses terahertz radiation very good. And the beauty of physics is on the left graph. When we check the refractive index of chocolate, it occurred that some chocolates have absorption peak and some don't. And the difference in between this red and violet, which correspond to dark chocolate, and this small and these three other curves, the difference is with milk, the presence of milk, and this is the peak of lactose, which is seen if we have absorption peak in absorption coefficient. So then we have this jump in refractive index. So in one funny project, we could demonstrate the beauty of physics that we can have in this terahertz range. And now, no matter if it is the middle or not the middle, more or less the middle, after the chocolate lens, I think it's a good moment for the coffee, especially that here we have like small scent that is more or less looking like terahertz range. So I think that we will make a, I don't know, maybe 5 minutes break just to grab a coffee, all the time thinking about terahertz radiation. So we can start actually from answering to the questions, because we have up to now 2 questions. If you have more of them, please type them in Q&A section. You hear me properly?
Yes, we hear you. Great.
Great. Yes. Okay, so the first question is, why is the peak moving to the right with higher thickness of the sample? I thought the peak will come from the first interface and should be at the same position as the ones from the thicker samples. I will go to the slide, because this is the question with this slide. Okay, if we have the peak of terahertz signal, so the dashed peak is the reference peak, so it means that it goes only through the air. Then if we are putting the sample, so the sample will attenuate my peak and will move it in this case to the right, so it will retard my peak because it is passing through the medium with bigger refractive index, so it is slower than the one that went only through the air. And now if we have the samples that have 1, 2, 3, and 4 millimeters, so then the delay of my pulse that is introduced is bigger and bigger, and as you can see, this the difference in between these pulses are equal, because the sample is 1, 2, 3, and 4 millimeters thick. The peak that is coming through the sample, reflected back and reflected back, so like twice reflected inside the sample, will be visible for this violet one here as this small tiny peak. Yeah, so this is the peak that is reflected back. This is the pulse that is transmitted through my sample, so the phase delay, like the delay of the pulse here is dependent on the thickness. I hope I answered the question. In case still it is not clear, we can contact and discuss more if you need. And now the second question is about materials for terahertz radiation. What about different ceramics? Different ceramics are also transparent. There is a photo of the kettle that you can see how much water is inside. And ceramics could also be used. I don't know how about manufacturing, but somehow I hope it could be also like if we talk about material, it could be also used. The next question, have you tried to fabricate kinoform on the other substrate like high resistive silicon substrate? I haven't, but group in FTMC they were ablating. I think that they ended up with 16 layers structure, so it is almost like a kinoform. And as I remember, it was for silicon, so I should check it for sure, but most probably they did it for 16 layers in silicon and using laser ablation. But here for silicon, we still have this big refractive index, so we should remember about these Fresnel losses we have. Okay, do we have more questions? Are there any losses other than Fresnel losses and absorption losses that can be dominant significant with thickness? This is easy and not easy question, because if we think about materials that are normal, I mean that if I have power and material, power of my radiation and material that acts linearly. So this should be the end of our, let's say, things to think about. But if we are having nonlinear materials, the one, for example, used in also in the time domain spectroscopy to generate and detect terahertz signal, so then we also have to bear in mind the dispersion inside the material, because it will have different time of, in easy words, it will have different time of flight for pulse of visible or infrared radiation and terahertz pulse, and then we will have with thickness mismatch of these two pulses, and the efficiency of generating the radiation will be much smaller. So in cases of, for example, nonlinear crystals used to generate terahertz radiation, also the dispersion should be taken into account. But this is not used as an optical element, but somehow it is also the material issue. And now another question is, the waving effect can be easier interpreted as the transmission of radiation via Fabry-Perot plane parallel plate. Yes, because it forms it is formed like Fabry-Perot resonate, like it is. How to call it? It could be understood as we have a kind of a resonator, but actually why we have this wave here is the fact that if we have the pulse here and the second pulse here, so this is the time domain, and if we go to frequency domain, so we make a Fourier transform. If we have a Fourier transform of two pulses, so the Fourier transform of 2 Dirac delta is the sine function. So that is why we have this sine-like function here. Of course, Fabry-Perot would have another reflection, but each next reflection is smaller and smaller. But even this small second reflection has the influence in this wavy-like structure. So I hope it was a comment question, but also nice to have. we'll go to the slide with the coffee and wait for, I think we end up with questions. Okay, in case you will have more questions, so please just ask them. Okay, so after the coffee break, we will go to different types of diffractive optical elements. Types, I mean the different way of possible beam shaping that can be realized by our elements. And now, in the easiest, in the next following slide, we will use the easiest setup. We will have our optical element, and we will actually examine the intensity distribution in a focal plane. Typically, if we would put a converging lens here, we will have a focal spot in the focal plane. Here is our optical experimental setup with mounted different elements. And what kind of elements we can design? Different. At the very beginning, we will discuss lenses that are made with a printer using paper or laser cutting of paper diffractive optical elements. And you will see that such kind of elements can realize different focal curves. So the first one, we will talk about elliptical and hyperbolical lenses. One is binary, one is kinoform, so we see here continuous phase profile. And the second, this is also a continuous phase profile, so this will have much bigger efficiency than this. And two elliptical structures, they are named by the shape of the phase delay introduced by the element, which looks like an ellipse. And such element would form in the focal plane here an section that is, we can choose the length of this section that is perpendicular to the optical axis. So here we have the phase distribution of our element, and here in the focal plane we will have the section perpendicular to the optical axis that is smaller than the size of the element. If we will have kinoform structure, then we'll have a little bit more energy here, and if we would compare them, the binary element is just having more or less half of the energy in the focal line segment than our kinoform structure. If we would think about hyperbolic structure, so it looks a little bit different, and it is also forming a line segment perpendicular to the optical axis, but this line segment is bigger than the element. So actually I should plot it like this. This is the phase distribution introduced by the element, and this is the simulation of how our line segment will look like. And such kind of elements could be used, for example, for different scanners, because they shine with, like, they illuminate the whole line at one point. If we would have experimental evaluation, so we would get the line like this. Now we also can have element that we call a toroidal structure, and this will form the circle perpendicular to the optical axis, and this the size of the circle can be chosen. And here there is some interesting issue with such kind of elements, because if we are laser cutting them, so we must somehow introduce some suspension bars just to hold the element in one place. And if we are making simulations, so we must incorporate the fact that our element will have these suspension bars. So if we will perform the simulations, we will not have very, very nicely round circle. We will see the influence of these suspension bars. Of course, we can make them random to reduce this effect. And if we compare theory with practice. So if we have our already laser cutted element, so this is this on the left hand side, we can see the simulation, how our focal ring would look like. And on the right hand side, we see the experimental data, and we see this influence of these suspension bars. And now, if we have, we also can have elements that are forming a line at some angle to the optical axis. And this line for the element that had around 13 centimeters of the size, after 42 centimeters, we could still see the line, and it was not very bigger in diameter than at the beginning. So this is also, in my opinion, interesting type of element, and we are able to calculate here the phase delay that should be introduced to redirect our radiation. Also, some element that is similar to this ring-like structure is a spiral structure. So such snail-like structure will create a donut. I magnified the middle of this intensity distribution. So after such structure, we would see in the focal plane kind of a donut. And what is interesting in such kind of elements is the fact that they are forming here inside optical vortices, because here we have phase discontinuity, that in phase inside here we will have this the same phase discontinuity as here, and depending on the design it can have different orders. So this type of elements are also present in terahertz world. Now, now we also can have non-diffractive beams. So we have Airy beams and Bessel beams, and this is the cross section after the element of the structure forming vortex beam. So here I have my element, and here is the XZ plot of the radiation for different types of structures. And with these red lines, we see the cross section that are given here below. These are XY cross section. So you see in each next plane how the beam looks like. So if we want to have our radiation to be elongated, so this is one of the methods. Here we would use Axicon structure to create a Bessel beam. If we are thinking also about Airy beams, we should analyze that if we will cover part of our element, so still it will have a similar functioning. Oh, I got the question and I stopped. Okay, questions at the end. Maybe not. What software, CST, console, or language library are you using to simulate your optical elements and TDS pulses to compare with experimental? What challenges exist in comparing simulation to experimental and making this more realistic? Okay, I'm not using CST or console. We can use it, but it takes quite a lot of time. For diffractive elements, we are using the program that is written by our professor from our faculty, which uses propagation using modified convolution approach. So this is a method that assumes that the output light field distribution is the input convolved with the pulse response of the of the air gap. Yes, so it is much faster, and then we end up with amplitude and phase distribution of my after some distance. Yes. You will get this also in the CST or console, but it will take probably a little bit more time. You can also use this modified convolution approach and write it in Python. It's not a problem. Actually, this one were generated not in our program, but in written one. So it takes not much time. And TDS pulses, it's totally different manner, because in TDS we are analyzing different things. Yes, if we are analyzing the radiation after our optical elements, we would mostly use continuous wave sources and detectors that detects intensity of my radiation, and we are raster scanning the distribution. If we are using time domain spectroscopy, for my research, mostly to determine material parameters, and we are using TeraView system. So this has it's built-in software. However, also it is not very hard to determine the power spectrum density or other parameters out of registered pulse. What challenges exist in comparing simulation to experimental and making this more realistic? What challenges? We would like to be able to make such simulations that correspond to the experimental data, experimental measurements. For challenges for me in terahertz wave using in terahertz range using wave approach would be the fact that the diameters of the elements are relatively small in relation to the wavelength. We will talk about it a little bit later, so somehow I will answer this question in the next slides. Okay, so we know that we can have different types of shaping the radiation. Also, we can somehow split the radiation. So one of the examples is using Daman grating. It's a binary grating that forms particular number of points at in this case in infinity. These Daman gratings can be used in one direction, in two directions, and we can form different number of points at particular plane. Of course, we have some additional points around, which are like higher order points, but this number of points that is calculated here, this like 1 to 5, these 5 points would have the biggest intensity. And now if we would like combine Daman grating with lens, so it will, here we will create 3 points, here we will create matrix of 3 to 3 points, and this number of points will be created in the focal plane of the lens. So somehow we can split the radiation. And now if we don't have analytical equation that we can have, that we can describe our element, so we can try to use kind of holographic approach, and we can iterate in between two different planes to create the phase distribution that will form particular intensity distribution. Here is the example that this element is forming across, the second one is creating 2 letters. So even if you want to illuminate our like to have some particular light field distribution at some particular plane, so we can calculate what should be the phase distribution introduced by my element to form such intensity distribution at particular plane. This is simple hologram. We can also make it more complex, because we can try to do 2 different images. Here it was very big challenge, because one of the images should be in one plane, the second one in the second plane, and all these the two elements were coded in such phase delay map, and this is the manufacture element. And now here we have the comparison of simulated and experimental data, and as you can see, they somehow correspond, somehow almost, because here we see some additional interferences, two different setup with two different scaling to like have the smaller scanning plane. In one plane we see the rectangle, in the second one we see cross. This outer part of crosses are actually almost not seen. But what we should still, I think it is a very, very big success of terahertz optics, because if you would see here, this element has a particular phase distribution that was 3D printed. And if we will compare the size of the element with the wavelength, so this element consists of 57 wavelengths. If we will think about visible light and we will think about pinhole, so the element that we assume creates me a divergent wave, so we call it almost a point source. So a typical pinhole is 20 micrometers for visible light, 0.1 micrometer, 0.5 micrometer for greenish light. So it will be 40 wavelengths for something which we call a pinhole. And here we have 57 wavelengths element that forms me two images at two different planes. So somehow it is remarkable that we are able to shape the light with such actually small elements in relation to the wavelength we are using. And also we can try to use neural network design. This is the example of the element that will form a focal spot. Here simulation, here the phase delay map of the element of the typical structure, and here we will have the element that was proposed by optimized by neural network. So we can see that it is not easy to guess what this element would do, but it focuses also radiation as this one. Now we can use also neural network design to redirect the radiation of axis. So here we have optical axis in the middle of my element, and we can see that if we are using theoretical iterative or neural network design, so here these two spots will be small, and we will not have this this middle spot as we slightly see here. Such elements can help, but also such a neural network approach can help, but also as you can see, this structure is it has very, very big phase discontinuities, so it is not so easy to manufacture as much smoother like this. So there are always advantages and disadvantages. Nothing is for free in life. Now we know that we have whole variety of different possibilities to design different optical elements, and these are types of them. So we can actually, with diffractive optics, freely shape our radiation. Actually, this is a small conclusion after this diffractive optical part, that we can use 3D printers to manufacture these elements, to use them, and to prototype easily. So this is a very, very powerful tool that is available in terahertz range and is much more expensive in visible optics. And now if we'll go here in what we can do and what we can't do with our optical elements. What we can do, we can compensate the incident beam. So we don't have to assume that our element will be illuminated with a plane wave. We can assume that it will be illuminated with divergent wave, we can shape our radiation in different forms. The thing we cannot the divergence of our source can be corrected, and we can incorporate it into one element. So this is also a big advantage of diffractive optics. Now, if we are talking about terahertz optics, mostly we would use off-axis approach, and here is the phase transmittance that I gave you at the beginning. This is for off-axis element, this is for on-axis element. So this uses paraxial approximation, this one not. And now, I know this is a very big table, but paraxial approximation is like you assume that, in easy words, you assume that the angle, its sine and its tangent is the same. So as we can see, up to 17 degrees, we have difference at the third place of comma in between these values. So we assume that paraxial approximation works up to 17, 18 degrees. And now if we are creating a lens using these two formulas, for if we have some diameter of the lens and big focal length, so then the difference, for example, for big focal length, the difference between paraxial and not paraxial approach design will be also almost none. If we will go to closer focal length, so we are increasing these angles, so we see that at the edges these functions start to be different. And if we would go here with 100, so these are not possible to image. Even here it's tough to analyze, because we have a lot of moire effect because of resampling to it on the screen. If we have very big angles, so these differences will be bigger. So we must use off-axis approach. And now close distances, because we have small focal lengths, for visible light, if we have 10 centimeters, we will have hundreds, thousands of wavelengths. For terahertz radiation, 10 centimeters will be, for particular wavelengths, 300, so hundreds of wavelengths. So all these angles in our setup starts to be relatively big. And especially in terahertz range, in many cases, we have a similar diameter and the focal length same. So this introduce already large angles in our setup. Or if we are focusing out of the optical axis, it is also case of bigger angle. What we should think here as well is the shadow effect, because if we design our element, so we must know that if we are illuminating our element from this structured size, so somehow some radiation can be redirected in the wrong order. If we will illuminate it from substrate range, so then we will redirect it in a good manner. If we will illuminate our element at some angle, also here we have some region that we are losing our energy. And what we should also remember about is the uniformity of the beam that illuminates my element. Because in many cases, we are not having ideal plane wave, we are having kind of a Gaussian distribution, like a beam that illuminates my element. And if we will think about it, so here we have a plane wave, here we have the focal spots, and here we have magnified them just to see, with some artifacts from, unfortunately, from graphical files, but still it is visible. So if we will have illumination with a plane wave and with a Gaussian beam with a smaller diameter, we see that the focal spot size grows, because if we have smaller diameter of my beam, so then my focal spot will grow. And here there is the example of different illumination for our toroidal structure. So we can predict what will be the difference if we will not illuminate our structure with a plane wave, but with a Gaussian-like intensity with smaller and smaller diameter. So somehow we can predict what would happen if we have too small beam. And the next thing that we should really bear in mind by describing terahertz optical setups is the fact of the existence of diffraction. So if we would have the object like here, so the image of such object will be flipped-flopped. This is the simulations for 0.3 terahertz and 75 and 50 millimeter diameter lenses. So if we would assume no aperture, we would result in the image that is just flipped-flopped. Here we slightly see some diffraction effects, but in reality, we would use mirror, which is 3-inch or 2-inch. And then you see these concentric rings that comes from the fact of the size of the limited aperture size. And this is something we cannot omit in terahertz radiation. This is very, very prominent, and in many cases we are fighting with such diffraction effects. And it is due to the fact that in comparison with the diameter of my element and the wavelength, we are in many cases in a closed zone. So the closed zone is the zone when we have a lot of actually diffraction effects and a lot of phenomena that are changing my intensity distribution. And additional thing that is here my problem is that in many cases we have sources with very, very big coherence, so we have unwanted interference effects. And now we will go to the imaging setups fastly, I hope, because this is something to comment. In many cases in terahertz range, we are taking the radiation, focusing on the sample, and then refocusing on the detector. If we want to do anything with our beam, so then we need another focal plane here. So the image would be obtained with raster scanning of like shifting my sample here in XY and obtaining the image point after point. And the resolution comes actually from the focal spot size of this lens or mirror, depends what we will use. Such kind of setup is good for terahertz range because it uses the main optical axis, so we are minimizing the influence of these diffraction effects. But not in all cases. If we want to manipulate with our imaging system, if we would need to introduce some filter to, for example, increase the possibility of imaging of transparent objects by spatial filtering, so then we need to do some filtration, and such setup not always is able to perform proper filtering. So what we can do more, we can try to illuminate our sample with a plane wave, then then introduce the filter in the focal plane and have the detector also in the optical in the middle of the optical axis. And here we have more possibilities to use different filters. If you're interested more, we can discuss it further, what types of filter perform which output like features. if we will look at the results of such imaging, so in the first setup, we see that this resolution is much bigger because it comes from the fact that we are focusing on the sample. If we are using only the middle of the setup with a plane wave illumination, so then we have a little bit more blurry image. And here the next columns are the result of using different spatial filters in a focal plane in the middle. So we can see that some parts that are relatively transparent can be here distinguished. To perform really proper phase filtering, spatial filtering, we would need to form in Fourier plane the exact amplitude and phase distribution of like the exact Fourier transform of my input image. So here I would like to have the amplitude and phase distribution that is a Fourier transform of my object plane. So what I have in the at the input. In such case, this setup illuminates the whole object, and then the image is formed in the plane. So we are not shifting this object, we are having the image at the output, and here if either we can have a matrix of detectors or we can raster scan our image that is formed instantly in the whole plane. But such system must have much larger diameter lenses, and here is the example. These lenses have 30 centimeters diameter. Our images were around 7, sometimes 15 diameter objects that were illuminated with parallel beam here. Here was our object plane, 2 lenses, and scanning with a detector. And now here we can perform different types of spatial filtering. And if we have a transparent object, so introducing different phase delays, but being transparent, we would see different results. And now this is the object. We have two different materials. One 3D printed material, the second one like polypropylene or something which is transparent, and the holes will infiltrated with paraffin. So if we would perform reference image, so it means without filtering, we would see uniform distribution. If we would use different types of spatial filtering, we would increase this, the possibility of imaging different refractive index values here and here. And you see that using different methods, we see this spot here, which is different than the background. In case of cross-like structures, already in reference, we could see these lines. So here it is, let's say, tougher to distinguish, but still, if we would compare the intensity in the background and inside the cross, they are much different for using spatial filtering than without. And now, if you are able to perform such imaging, we actually know that this type of setup will perform image like a real image, not raster scanning, but it requires big apertures due to huge diffraction. But still we can see that it enables us to visualize transparent objects. Now I will jump to the last part of the presentation, and this will be a small like application of elements to for particular reason. I would like to introduce you the system that has that is realizing multiplexing and demultiplexing of terahertz radiation by diffractive optical elements. Here we had 2 different sources. We wanted to combine them within one source For some reasons, we decided to make a focal spot after the element to design this element in a most efficient way. Then we were using collimating lens to form a plane wave, and it could propagate into our system. Here it is a little bit smaller due to the size of optical table. And after this collimating lens that was propagating our signal at some distance, we were using structure that would demultiplex two signals and redirect them at two different detectors. Here, because we were using frequencies that were only 1 gigahertz, had 1 gigahertz difference, so we were using additional diffraction grating to properly separate them at finite distance. And now these were the designed elements, the one multiplexing, like so gathering the signal from two sources. This was the element that was splitting and additional grating to help proper splitting. And the bottom, these are the manufactured elements. So if we would look at what is happening after the first structure, so this was a multiplexing structure, and the focal spot by illuminating with only one source, with the second source, and with two sources. And this is the these are the focal spots formed just here after the structure. So if we would think what is happening here after the collimating lens, so here after we are more or less here in our setup, so we see that we have one source, first source, second source, and two sources, and we have the XY cross section 5 centimeters after, 20 and 35 centimeters after. So we see that we have a parallel beam propagating along optical axis, and you can see here this present diffraction effects. If we are after our second structure, so our demultiplexing structure, so actually we can see that using one source we have the left dot, using right second source we have right dot, and if they are two of them are shining, they are still separated and can be detected. And with this, I would like to make some final conclusions that with diffractive optics, we actually can shape the beam in almost unlimited way. Reflective optics is like wavelength independent, so this is very, very powerful feature here in terahertz range as well. And if we have very high energy beams, we have problems with materials. This is more the problem of X-rays and UV than terahertz, but still we must somehow have it in the back of our mind. And in terahertz range, we have a lot of transparent materials. Some of them can be 3D printed and used as optical elements. So it is like a paradise of an optical person to be able to design and manufacture whatever we need. We also can try to use neural networks to help to optimize different optical elements. And what we should think about is that almost always we need to use off-axis approach. We need to take in mind that we have big diffraction effects, and for many continuous wave sources, we will have very, very big unwanted interferences in our system, and this kind of Fabry-Perot resonator in between our elements. So this is something we should have in the back of our mind. And here is my email. So if you have questions that are still not asked at the Q&A section, so please don't hesitate to write. I see that we have already 2 questions. So I will try to answer them now. Do you have infrastructure to cover the substrate with a gold layer, or you send it somewhere? We have infrastructure at the faculty to cover with gold, aluminum. This is not my group, but we are cooperating together. So we can cover we covered terahertz 3D printed mirrors with aluminum and gold in our faculty, but also we send it to another company that just put aluminum a thicker layer. I can print them, but still I would need to send it somewhere to cover it. I don't polish 3D printed elements if they are if we want to use them for smaller terahertz, like this sub-terahertz range, so there is no need to polish. If you want to polish, to use it for higher terahertz range, you should do it. But then remember that by polishing, you can also change the shape of the surface. So not always it can help. If you're interested in the company, I can also send the one that we were sending, but please write me an email because I don't remember it by heart. And the next question is, what about the active elements such as AOM, EOM for terahertz? Do you use them? What are their effectiveness? I'm not using them, but in general, you can. About the effectiveness, this is always hard question because it depends with what you're comparing, yes? So it is like even in between diffractive elements, we had the discussion like what is the efficiency, if it is effective enough or not, and still we have here problems to compare. So in between two different actually devices, it is hard for me. Maybe someone who is using would answer it better. But for me it's hard to compare because I wasn't using them. Maybe still, but maybe there is open question to use. The next question is, does the Dou operation depend on wave polarization? In general, designing optical elements, we don't assume we don't introduce the polarization of the radiation, but somehow in the whole setup you will have the dependence on the polarization because many sources are linearly polarized. The Dou itself doesn't depend, but you will somehow have the problem of polarization in your optical setup if you have linear polarization and your detector is sensitive for some particular polarization. So here we must know that we have this kind of polarization, but Dou itself wouldn't change it. Unless you will use some nonlinear structure inside, so like some liquid crystal or something in this way. So then you can design a diffractive optical element somehow with a liquid crystal, so then it would also affect polarization. I'm thinking about one thing to comment, because for this higher terahertz, if we are using 3D printing, so sometimes we see that these lines are somehow like they are not smooth enough for higher terahertz frequencies. So these are this is the range that we are rather not applying 3D printed elements. But because we are lacking actually in resolution. Okay, any more questions?
Let's give maybe one more minute for everyone to
we will
take it all in and ask a question. Oh, I see that Professor Abramski wants to pitch in. Okay, let's make an exception and allow Professor to speak with us.
Of course, if some question was, let's say, you had the other question that, or I haven't answered what you wanted to hear, always you can write an email, because sometimes it is hard to guess, like, about what is the question. Like,
it's always good to have the opportunity to ask questions later. Yeah, I agree. Professor Abramski, you can ask your question if you want. You raise your hand.
Maybe unintentionally.
Oh, maybe it was a mistake. Well, okay. Oh, maybe.
Yeah, sorry, I wanted to react in a positive way, but I I changed the position. Sorry.
Okay, no problem. Thank you for this nice comment. Okay, then. So if we're done with the questions, let's thank again Agnieszka for this amazing lecture. And yeah, next week we will have our last lecture in this series. It all went so fast, I don't even know when. So the next week's lecture will be given by Gintaras Valousis. I'm hoping I didn't butcher the name, who will tell us a lot about terahertz imaging towards compact and effective systems. Okay, so thank you very much, everyone, for joining us today, and have a great day. Bye-bye.
Have a nice day.